Okay, so hello everyone. Today we'll be going through all the forms, the various kinds of the Gaussian integrals that there exist. They're quite handy in statistics, in physics, and just generally interesting in the way that they relate the exponential function, the Euler number, to the number pi. So, firstly, we'll begin by introducing the normal Gaussian. The normal Gaussian integral is written as the integral from minus infinity to plus infinity of the exponent of minus x squared dx. So to solve this integral, you can check that it is not solvable by usual means. Okay, you can't apply integration by parts and similar methods in order to get a simple trivial solution to this integral. Therefore, you need to get smart. And the best way to get smart in this case is by using something called transformation to polar coordinates. It isn't actually called transformation to polar coordinates, it's just called polar coordinate substitution. This integral, firstly, is given by the area under this curve, right? It's a bell curve. It's very common in statistics. And as you can see, this bell curve is very symmetric, right? So this thing is equal to this thing, and the areas under this curve is the integral. So here we have minus infinity, here we have plus infinity. So if we have this integral, let's call it I, right? I is also equal to twice the integral from 0 to infinity of our exponential function. Therefore, we can just see that if we calculate this area and multiply it by 2, we get this area plus the area of the other part of the bell curve. Okay, so now we can start actually solving this integral. Let's introduce a second integral, right? With the only difference being that instead of x, we integrate it with respect to y. Now this will come in handy just in a second. If we multiply, let's call this I of y, and this is I of x. If we multiply I of x by I of y, we get the integral from 0 to infinity of exponent of minus x squared plus minus y squared dx dy, which is equal to the double integral from 0 to infinity of the exponent of minus radius squared times the Jacobian dx dy. Or in this case, dx dy become dr d phi, where phi is an angle. Now, let me explain why this happens. So r here, we imagine it as some radius. If we have a circle is given by the equation x squared plus y squared is equal to r squared. And x in this case would equal r cosine phi, and y would equal r sine phi, such that by the Pythagorean identity, cosine squared phi plus sine squared phi equal 1. We can just, by substituting these transformations, factor out an r. We have r cosine phi sine cosine phi times r. We can factor out an r times 1 is equal to r, right? But r would be squared. So it is just a note. And phi would just be the angle corresponding to a cosine value, which isn't specified, right? It's just an abstract function that has no value, no real value. It is just used in order to fit it well within the scheme of polar coordinates. So now the Jacobian. The Jacobian is basically a determinant. It is a determinant of the partial um, derivatives of our initial coordinates just with respect to some other coordinates in which we transform our coordinates to, right? So in this case, for example, we're transforming our x and y Cartesian coordinates to polar coordinates, r and phi, radius and angle. And what this means is that we go from a normal Cartesian coordinate system, right, that has 90-degree angles, to a coordinate system which is just a bunch of circles, right? And our coordinate x, for example, this length x, right, it becomes curved, right? It becomes equal to radius times cosine of phi. Therefore, this stretching, I'll just keep this graph in order to help understand the viewer why there's this transformation, right? See, grids in a normal Cartesian coordinate, they become curved. And this curving is the transformation of area. And the transformation is of area of, say, 2 by 2 matrix, x, y, x, y, is given by its determinant. It's, if here we have x1, y1, x2, y2, we have x1, y2 minus y1 times x2. It's the transformation of area of our initial parallelogram formed by our vectors in the matrix. It's basically the volume, not the volume, it's the area of the parallelogram formed by the vectors of a corresponding matrix. Right? Yeah. So to calculate the Jacobian, we just need to take the partial derivatives of x and y with respect to radius and angle. So we'll have partial derivative of r cosine phi divided over del r sine phi over del r cosine phi over del phi and del cosine, del r sine phi over d phi, straight line. This would just equal to, well, here it's the determinant of cosine phi sine phi minus r sine phi r cosine phi, which is equal to this times this, which is r times cosine squared phi minus r times minus sine squared phi, which is equal to plus r sine squared phi, which is equal to r. So we end up with an integral from 0 to infinity, the double integral of the exponent of minus radius squared times r Jacobian, times dr d phi. Now, by the Fubini theorem, we can split this into two integrals, or we can just first integrate it with respect to the radius and then with respect to the angle, and we will get this. Now, this integral, it is equal to, wait, I forgot the r, here we need to multiply the r. This will just have minus exponent of minus r squared over 2 from 0 to infinity, which is equal to 1 over 2. And our coordinates with respect to phi, they'll change from 0 to infinity to from 0 to 2 pi, because while on the number line we have plus infinity, right, when going up and sideways. In a number circle, right, in a circle, we only have 2 pi radians. 2 pi radians. So the infinity equivalent for the angles would be 2 pi. So we'll just have 1 over 2 times the integral of 1 d phi, where instead of infinity we'll just have 2 pi, which is equal to 2 pi over 2, which is equal to pi. And this is equal to ix times iy, where ix is equal to the integral from 0 to infinity of exponent of minus x squared dx, which is equal to 1 over 2 of just the Gaussian integral, right? So the Gaussian integral squared, right, because the transformation over coordinates does not matter, right? It is just the same as ix times ix, which is ix squared, over I of g is equal to pi, meaning the Gaussian integral is equal to the square root of pi. Good. And then the integral from minus infinity to plus infinity of the exponent of minus x squared dx would be square root of pi over 2, because our I of g is equal to this integral, which we'll call just t. I of g is equal to t over, twice t times 2. Good. So this is our standard Gaussian integral, very easy stuff. Now let's go to a generalized form of the Gaussian integral, which is given by the integral from minus infinity to plus infinity of the exponent of minus ax squared dx. We will just apply the same method, right? By transforming it to polar coordinates and stuff, we'll get the integral from 0 to 2 pi d phi, the integral from 0 to r, or 0 to infinity, to infinity of the exponent of minus ar squared times r dr. Now, the key point in this integral, in solving this integral, is to just solve this expression. To solve this, it's quite trivial. We can just see that this is the same thing as for the Gaussian integral, right? It will just give us 1 over 2 minus 1 over 2 exponent once ar squared. But since we have an a term, just some parameter a, also in this stuff, we'll just divide by a again. Not again, but yeah, we'll divide by a. Therefore, our integral will transform to the integral from 0 to 2 pi of, we can factor out the constant, of the exponent of minus ar squared d phi, where here our r is going from 0 to infinity. This will just equate to minus 1. So we'll have minus 1 d phi, giving us 1 over 2a times 2 pi, which is equal to pi over a, which is equal to it will be more appropriate to do this because, yeah, it's squaring, just how we did in the other method. Yeah, like this. I apologize for the minor mistake. Yes. So this is equal to I sub g, gg, Gaussian generalized, right? This is equal to I gg times 2, and here it's squared. Therefore, I gg, our generalized Gaussian integral, will equal pi over a times 1 over 2. Good. So this is the most common form of the Gaussian integral. It is the generalized Gaussian integral, right? Because it covers basically all cases. Just a needs to be bigger than 1, or equal to 1 actually, since in the case where a is equal to 1, we'll have the Gaussian integral. Otherwise, if a is negative, we'll have a very improper integral. It won't just don't sum up to anything. Now, from the generalized Gaussian integral, we can also talk about the shifted Gaussian integral, which is given by this equation, where we have still this parameter, and we have x being shifted by some number b. This is quite easy, because if we can substitute x minus b is equal to u, dx will just equal to du, and we'll solve this integral. It will just be pi over a times 1 over 2. Now, in regards to complex analysis, or rather not complex analysis, but complex integrals, where we have the imaginary number, we can formulate the Gaussian integral for complex numbers, which is given by the exponent of I times ax squared dx. This integral is very often found in complex analysis. It is very often used in quantum mechanics due to its usefulness in oscillatory systems and stuff like that, and due to the connection of the Euler number with cosine and sine. It is very useful in the way that it can describe oscillations that are given by trigonometric functions. The complex generalization of the Gaussian integral can be derived as follows. Now, we'll just start off by labeling our a is equal to integral from minus infinity to plus infinity of I times ax squared, or sorry, I need to put a minus term. Otherwise, it's an improper integral. Complex analysis, where complex numbers are often denoted by the letter z, we'll use z is equal to ix squared, or rather, we will denote z is equal to square root of I times x, right? Or square root of ax, we'll denote z as being equal to the square root of ai times x, so that x, I apologize. We'll denote it equal to square root of I times x, which is equal to square root of minus 1 times x, such that z squared is equal to ix squared. we'll take that the real number a is bigger than 0, and we'll recall that for a shifted Gaussian integral, we have Gaussian integral being equal to as we have already solved, it is equal to square root of pi over a times 1 over 2. Good. Now, if we assume that square root of a is complex, right? And square root of a is equal to square root of the absolute value of a times the exponent of I phi over 2, then our solution to the Gaussian integral, generalized Gaussian integral, will become square root of pi times the absolute value to the negative 1 over 2 power, so square root, right, times or over the exponent of I phi over 2. The complex shift, yeah, we have already described that. So for complex numbers a, we'll have that the Gaussian integral is equal to square root of pi over absolute value of a times exponent I phi over 2. Otherwise, we can also describe it using an elementary first order differential equation by setting I of a is equal to the integral 0 to from minus infinity to plus infinity of exponent of IA of x squared dx. By differentiating with respect to parameter alpha, we'll have the partial derivative of this integrand, which gives us the integral of I of x squared exponent of a x squared times I dx, which is by differentiation by parts equal to I of x exponent of I a x squared over 2 minus the integral of exponent of I a x squared over 2 dx minus infinity plus infinity, and here we have limits from minus infinity to plus infinity. This just oscillates back and forth, and this just basically we can disregard it as 0. Here we'll have also the I term, and we can just see that the derivative of our integral function I of a is equal to minus I over 2 I of a, right? Because here we have just minus I over 2 of exponent of I ax squared dx, yeah, which is equal to minus I over 2 of I of a. By solving this first order partial differential equation, not partial differential equation, what am I talking about at this point? By solving this first order differential equation, we can get a very easy solution, right? It is equal to I of a is equal to a constant times exponent of minus a times I over 2. This is easy, but generally speaking, by using contour integral arguments, right, we can just say that I of a is equal to 1 over square root of a times the integral from minus infinity to plus infinity of exponent of I z squared the z, such that z is equal to square root of a times x, and dz is just equal to square root of a times dx, which is equal to square root of pi over a times exponent of I pi over 4. Yeah. So this is the basics of various types of the Gaussian integral. Yeah.